And you want to do it with minimal effort. If you don't walk too far away from the laptop. And of course you want it to be responsive. Responsiveness is everything in these applications. If you have an animation that's running at 60 frames a second, and then for some small part of it, it drops down to 30 frames a second for any reason, whether you've created too many objects and the garbage collector is running. Maybe it's better to run that entire animation at 30 frames a second, because the human brain is just fantastic at spotting glitches in anything. So if you can't iron it out to make the whole thing 60 frames a second, just drop it down to the frame rate that makes sense for your application. Keep it responsive. Make sure people have a high quality perception of your application. They feel like you put the effort into it. So there's all sorts, as I say, of different ways of rendering on Android. The first one is the canvas. The canvas class is that super flexible thing that's been in all the versions of Android. Most of the Android UI was done with the canvas class. It supports lots of different operations. From the canvas class, you can access OpenGL for a surface view. There's also Renderscript, and then there's the NDK. All these different things come together to enable you to write mega high performance applications on Android with minimal effort. So let's start with the first one. The NDK and OpenGL ES. Why are you using the NDK? The NDK is like the hardest thing to do in Android. But of course, if you've already written a game, maybe for Xbox or iPhone or something, and you're trying to port that code base across, the NDK is a superb way of doing that. You can just take the code almost straight across onto the Android platform, do a little bit of glue, do some Dalvik kind of memory systems, and with the NDK, OpenGL, and native window, that's the combination that gets you the highest frame rates. The native window gets you onto the frame buffers, pixel pushing on the GPUs. That's what it's there for. We have some applications that use this powerful combination. You can do the floating point processing at the same time as natively accessing the OpenGL APIs. This is super fast. And one great example of an application that uses it is Google Earth. This is a native window. It's doing lots and lots of mass processing at the same time as doing 3D rendering. And if you're going to push that amount of throughput through a device like this, through a tablet, you're going to use native window, OpenGL, NDK. Of course, it's all done through OpenGL. You know OpenGL. You can use OpenGL now through the canvas layer, through Surface View. You can use OpenGL through Renderscript, and you can use OpenGL through the NDK. And why are there three different ways of doing it? Well, if you look at the canvas class, every single OpenGL call that you make has to go through the JNI layer, down to the native layer, and back up again. And that takes time. Every single setup, every triangle, every point goes from the Dalvik layer to the JNI and back again, if you're doing it on a canvas surface view. If you're doing it with Renderscript, you can tell it to execute all of that OpenGL natively, and if you're in the NDK, of course, the same. So, the OpenGL is closest to the GPU hardware. You get those frame rates. And people use it for 2D graphics as well. Things like that sheep and clouds game that we saw earlier today. That was surely OpenGL. So the easiest way of doing it is this, Canvas plus OpenGL. You get to write it all on the Dalvik layer, all inside your Android application. You get some really good frame rates. But as I say, once it's doing it, every single OpenGL call you make is getting passed through the JNI layer and back again. So if you find yourself stuttering and losing performance, you've got to consider porting that OpenGL code down into the NDK. But a good example of an application that did this, it uses a surface view with OpenGL, which is the simplest way of using OpenGL on Android, is Google Body. Really nice application, super fast, all written in the Java layer, you can spin it around, change the levels, things like that. You can tell it's not like super complex, there's not big backgrounds or lots of different textures happening. It's powerful enough to run this from the Java layer through to the NDK. But if you miss having pointers, if you're a hardcore geek, and you fancy some fancy graphics, but you don't want to use the NDK, then we have something relatively new. We have Renderscript. And in Honeycomb, Renderscript was used in a few different places. It wasn't that well documented. It's a little bit better now with Ice Cream Sandwich, but it's really nice that these Ice Cream Sandwich devices, like the Galaxy Nexus, now all support Renderscript. So it's not just for tablets now. Anything from 3.1 upwards, you can add a hero screen into your application with Renderscript. And again, that's going to improve that perceived quality of your application. I'm going to run through a Renderscript demo very soon. And the nice thing about Renderscript, there's another one there, the YouTube board in Honeycomb is also Renderscript. The really nice thing about it is you don't have to use the NDK. You get to run your code on the GPU, you get to do super fast maths calculations on the GPU without writing too much glue code and without mucking about the NDK itself. And of course, like with everything else, you can access OpenGL through Renderscript. Much easier to glue to the Dalvik code than it would be if you were using the NDK. Again, slightly challenging to debug. Any code that's going to run on the GPU is going to be harder to debug. And the GPU manufacturers do produce tools that make it a little bit easier, but it's tricky, right? Only when it's running all of the software can you get full debugging on these devices. But the killer thing about Renderscript is that it works across different CPU architectures with a single binary. And that's because you're not compiling it natively yourself, like with the NDK. With Renderscript, you write a script in C99, and you package it inside your APK file. It actually gets converted to bytecode for you by the compiler. There's an LLVL compiler with the emulator with Eclipse. And the Renderscript gets compiled to a bytecode. And then as it transfers to the device, on first run, that bytecode gets compiled natively for the device. And then it can take account of all the floating point architecture of the device, the vortex, different things on the CPU, vectors are on the vortex, the neon and the vector on the CPU. So you don't need to worry about it. You write the script and guarantee it runs across all these devices. And you don't need to limit your device, the devices that you're deploying to. And finally, just that slide on the OpenGL plus the NDK. The reasons why you wouldn't do it, it is the hardest way of doing it, but then the reasons why you would do it is it's the highest performance. And if you've got existing code, you can put it across. And finally, the native window. Just get straight into that pixel buffer. And it does require the NDK, but it's super, super, super fast. Okay. So that's the canvas, the Renderscript, and the NDK, and all kind of with OpenGL. You can see why you would choose each one of those. If you've got a pure Java application and you want to do some OpenGL, you can just do it on Surface View. If you want to make a hero screen in your application using super high performance, then maybe you just want to add it in Renderscript because you don't want to break the whole NDK out. But then if you've got a whole game that's coming across, put it through using the NDK. And that's why OpenGL has to be supported on every single one of these layers, because they have different use cases. And the canvas supports scaling and rotating and skewing and all kinds of different things. And the canvas is, as I said before, the most feature-rich way. It was using the Android framework since the start. And if you're going to use the canvas, it is the least performant method. So you're going to want to make sure you draw the smallest number of pixels on the screen, and that can be really tricky. You can end up writing a lot of code to reduce the amount of pixels you're drawing on the screen. I mean, if you're worrying about your clip rectangles and figuring out where things are and cutting the right things out so you can draw less pixels, it's your choice. If you're going to use the canvas, you may have to go to some of those extra levels to gain some of the performance that you've lost because you're on a canvas. But you've got a simpler coding environment. And of course, if you can, draw each pixel only once. And again, that's very hard, because people, when they get a canvas, they color the whole thing white, and then they draw a layer, and a layer, and a layer, and a layer. But as you're drawing all of those layers, you're wasting draw time. That's very rough. So try and invalidate the changed regions. Setting background thread to background. We've always advocated in Android, if you turn hardware acceleration on and you get some glitches, if you don't understand display lists and layers, then you probably won't understand when you've got the glitches. But if you know about these two things, It's going to be really easy to debug your code and make it able to run with hardware acceleration turned on. And as Nick mentioned before, as soon as you target API level 14, hardware acceleration is automatically turned on for you. So you just want to make sure you know about these things that we'll run through in a second. Make sure you scale through bitmaps. Not scaling bitmap and passing it to the framework can be really, really expensive because on every single refresh of the screen, it's going to rescale the bitmap and put it to the screen for you. It's not like the framework is going to see that at draw time you run a different size and then just cache the scaled down version. It takes the big version, on every refresh of the screen, it scales it down and yours, it scales it down and yours. So if you just scale it down to the size you want first and pass it in, you're going to save a ton of memory and a ton of CPU time. Really easy optimization. Okay, so we're going to run over to the LMI for 3 examples. One is just going to be a simple canvas, one's going to be OpenGL, and one's going to be Renderscript. Can we just turn this on, please? Thank you. Okay. And I'll run them on these two because now that we have ice cream sandwich, we can run Renderscript on the phone as well. So let's start with the stopwatch. Simple application, this. All it is a bitmap over there, on the screen, and then hands turning around. This is like 15 lines of code done on a surface view in the Dalvik layer. Really, really simple to do. Just grab a bit of clip art, stick some hands on it, and we'll run through the code in that in a second. You'll see it's a tiny, tiny amount of code. It's just one thread running through an update routine and a draw routine. Stop both of those. The next one's going to be the OpenGL. I'm showing you all now, before we run the code, the switching forward and backwards is going to be tricky. Just a simple texture triangle in OpenGL. How do you get that into Android? Again, it's not much code, especially if you understand OpenGL. And the third demo is going to be the Renderscript. So this is called the Renderscript fountain. It's an example that comes in the current SDK. And whenever you touch the screen, it produces hundreds and hundreds of particles. You can see that's falling down the screen there. Thousands of particles in total. You can do all 10 things on either screen. And the only reason we can get this kind of performance of all these thousands and thousands of particles being generated and thrown to the screen without using the NDK is because we're using Renderscript. So I'm going to run through how you can make that in Renderscript, and you catch the touch events in the Java layer in Dalvik, and you pass them to the Renderscript. And in these two examples, in this example here, this entire window is a Renderscript surface view. And a Renderscript surface view is like any other surface view. You can just choose to be a part of the screen, any kind of rectangle size. In this case, we're filling the whole screen with some Renderscript surface view. And the Renderscript is being told, whenever there's a touch event, to generate tons and tons of colored particles. Okay, so let's have a look at the code for those three. Robbie? Can you switch back to the laptop, please? Thank you. Okay. So, just shut this down quickly. I just realised I was writing some code before I came on stage. Here we go. Which way are you? Beautiful. Okay, so the first one, a surface view. The ultimate stopwatch that you just saw there. Just a simple bitmap on the screen and a couple of hands spinning around. If you want to make a custom component like that, it's simple. It's actually really rather easy. Here we have the surface view. And the main part of this is we have a thread. And whilst it's running, all we do is update physics and do draw. It's these two lines here. Around it, we've got this lock and unlock canvas. And the reason for that is if you lock the canvas to get it and unlock it afterwards, we do double buffering for you. Excuse me, you're going to get a much better frame rate, you're not going to get any glitches. So just calling lock canvas, and then doing some operations on the canvas and then unlocking it, creates that second buffer off screen, and when you unlock it, puts it back on the screen again. So you get some smoother graphics. So let's have a look at just the two methods. One is update physics, and all update physics does is look at the current time and figure out the angle of the two hands, the minute hand and the second hand. And after update physics is run, it runs draw, and that one there is draw. And it, like says it, does the background penalty white, controls the clock image on the screen, and then when you're using canvases in Android, if you want to take a graphic and put it on at a strange angle, you actually rotate the entire canvas, then put the bitmap on the screen and then rotate it back again. So here we draw the seconds hand and the minutes hand. So that's it. This little bit of code here is my custom component which gives me a graphical stopwatch. That's not too bad, right? It's just a thread pinging around. Somewhere I do a sweep here. Putting a sleep in it just to make sure that the touch response remains responsive, and I just max it out to around 50 frames a second because it's kind of fun. You can play around with these numbers. Just find the angles and draw them to the screen. And that just keeps running and running and running until you press the stop button. And the M run up here. There. Take this one. If running changes, you change the state. So it's quite easy with just a standard surface view to do a little bit of graphics. If it's not too complicated, you can get a nice frame rate, and it's very easy to do. The second one we looked at was the textured triangle spinning around on the screen. Similar. Okay, now we have a GL surface view activity, and all it does, let's see if you can see all this fine. You would have told me if you couldn't see it, right? Is set the content view to a GL surface view. And there's nothing else in there, just the on-pause point view. The GL surface view just sets the GL renderer. It does absolutely nothing. It sets the GL context to be OpenGL2, and then sets the renderer. And the renderer looks like this. And it's these methods that all start with GLES 2.0. But when you're using a canvas, all of these are getting passed through the JNI and back up again. So there's overhead for every single one of these methods. If this was done in Renderscript or NDK, this would all happen straight on the native layer and straight with OpenGL and GPU. But still, it's not that bad. We just have our renderer has a draw frame method, and the draw frame method looks very, very similar to the one we saw before. You clear the color, bind your textures, make triangle vertices on those OpenGL things. There's tons and tons of great OpenGL tutorials online for looking at figuring out how to do textures and loading meshes, things like that. And then we draw it. So again, not too complicated, and that's an OpenGL surface view. So it's the least performant way of using an OpenGL on Android, but it's there and it's quick and it's easy to do, and you don't need to use the NDK. And then the final one is the Renderscript. And just like we just saw the surface view and the OpenGL surface view, the GL surface view as well, now we have a Renderscript surface view. And our Renderscript surface view actually only has one method in it. It's got the onCreate, things like that. And you remember what I said, we have this surface view, which set it to the whole size of the screen, and then we're capturing the touch events. And we're passing those touch events through a small amount of glue to the Renderscript file, which we'll see in a second. So here you can see, on a touch event, we do mRender.newTouchPosition. And mRender is the glue. It's just a class which has one line in it to assign the script to the Renderscript in the creator, and then you can call mscript. In this case, invoke add particles. And it's that line there that's the glue. And the nice thing about Renderscript is, it's pre-compiled, as I said, to a bytecode in your environment, in Eclipse, and then it uses reflection to give you access to the methods. So control space, method lookup, inside your Dalvik code, here in Android, is working against the Renderscript. So you can find and look up method signatures for methods like add particles, which makes it really kind of easy to use Renderscript in this environment. And then if you look at the project structure, this thing's really not working very well. You have fountain.rs up there. And that's the Renderscript file. And you just leave it inside your package here. And this is what the Renderscript looks like on the right. This is the add particles method. This is when I touch it, and that touch is passed through from Android through the glue to this script. This is what runs. This is what creates those thousands and thousands of high-performance particles. This small piece of Renderscript written in C99 with your pointers, and you get your pixels. And as they're coming down, they spread out a little bit, and it chooses colors at the top. But that's what a Renderscript file looks like. And we have a ton of Renderscript examples, sample files inside the SDK now, and we have some better documentation, but again, it still needs improving. Not all the functions are exactly documented yet, but it's coming. And it's going to be a really nice way of adding those hero screens to your applications, and just making your application feel that one little bit better. You can think, how can I make my application better? You just add one screen in with Renderscript, like the music screen. It may not even be a screen that gets used too often, but it just gives that impression of a high-quality application on Android. Had anyone here, or has anyone here, used Renderscript before? No, that's good. I mean, why would you have done, right? It's only for Honeycomb and there was no documentation. But hopefully now we can start to see more Renderscript hero screens coming out. I say hero screens because writing an entire application in Renderscript probably isn't what you want to do. And you can find that if you look at the carousel example we open sourced in the Android UI utils, the carousel from the music application is open source, and it's a lot of lines of Renderscript. But the nice little touches, nice, really high performance things when you don't want to use the NDK, this can be a really nice way of being a hero. Or just doing some high performance maths calculations. It can be very easy to do that on the GPU with Renderscript. Okay, so up until ice cream sandwich, up until Honeycomb, but even more so with ice cream sandwich, previous it was a software UI. The whole of the UI wasn't accelerated, could be a little bit laggy. And now we've accelerated it all. We've done the UI on the GPU, or as Chet said it, he called it GPUI. GPU UI. But why have we gone and done that now? We've got these super fast tablets now. We've got dual cores, 1.2, 1.5 gigahertz quad cores, that Tegra 3 thing with 17 cores. It's got a quad-core processor, one core for when you're doing like high anything, like a little powered down core, and then a 12-core GPU, 17 cores, and a good battery life. It will be. I can't wait to get my hands on. That's going to be my next big toy as soon as the Tegra 3 comes out. But why have we suddenly gone and done GPU on the UI? Well, it's all about memory bandwidth. The number of pixels on the screen has outstripped the memory bandwidth. For software rendering, we can no longer put... What? Wow, did I just do that? That's kind of cool. Yeah. This isn't my clicker. I picked up someone else's clicker today. I didn't keep this one. The memory bandwidth has just gone. I mean, it's not got much faster, but the number of pixels we're pushing has grown massively. Even from the N1 at 800 by 480 pixels to these things at 1280 by 800, you can see the number of pixels that we have to push to the screen just can't be done with software anymore if you want any decent kind of frame rates. So even with all these faster processors, the memory's not getting that much faster, and we need to get down into the GPU. We need to be right there where we can render in 0.01 milliseconds, straight from the frame up onto the screen, with no time at all. So software rendering used to look like this. One draw, canvas draw, rasterize, display. And now it looks like this. We stick it across the OpenGL straight to the GPU and then to the display. So whether you're drawing a list, calculated in triangles or OpenGL, or a button, or a path, if you've got hardware accelerated equals true, it's going to go through the GPU. And if you want to test your app, on Ice Cream Sandwich now, there's an option in the developer settings called Force Hardware Acceleration. If you turn that on, every app has to use hardware acceleration the whole time, and we totally ignore this flag, which can actually be beneficial, and it's great for just testing your applications. You can tell hardware acceleration on and off in your application at absolutely any layer. It can be the application, the activity, the window, or any particular view. You can do it inside the XML, in your activity here, or in your application, or you can do it in the code. If you have a window, you can set the flag to hardware accelerated. Right down to the view, you can set it software or hardware. You can also check whether things are hardware accelerated or not, which can be very handy if you're not quite sure what device you're running on and you want to support a whole range of devices. You can decide what the best types of layers to use. Of course, we have caveats if you have hardware acceleration on, some things aren't supported, and that's mainly because we've done pretty much a one-to-one mapping of the canvas functions to the OpenGL functions. And if there wasn't an OpenGL function, it was quite hard to map it this way. So whether these are going to be backfilled later on or not, I'm not sure, but at the moment, none of these operations work on canvas. And then there's the limitations. These things, such little stars beside them, they do work, but we may ignore some features, or it may just work with text. Okay, so turn hardware acceleration on, try your application out, and if it doesn't work, then maybe this is why. The new drawing model. This is what I was talking about. This is display lists and layers. So here we go. The old model, a view root. You recognize what this is. That's the layer. You invalidate your views, it invalidates everything all the way up to the top, and then it redraws it all the way back down again. That's great. You don't get any inconsistencies on your screen, you get very minimal artifacts, you just have to invalidate anything, and the whole region around it will just get redrawn for you. Not particularly efficient, but there you go. It makes life easier. In the new model, we now have display lists, and when you're running through the draw, we're caching every single operation that has to be done to draw that item. And we cache it in something that looks like this. So this is the display list. And this has the measurements cached in it already. This is very, very quick to render. So if we cache one of these for your button, for example, then if we need to draw your button again, we can just run through this in a fraction of a second and the button appears on the screen. So this is the first optimization, display lists. And now, as we draw it the first time round, that's the drawing on the left-hand side, we cache the display list of how we drew it on the right-hand side. And now when we invalidate, we can just say, you've invalidated button B. We just mark it as dirty in the display list and just say, that part of the display list needs to be re-rendered. So we run back up and validate, it rebuilds the display list, which means all it has to do is rebuild a little bit for button B. And then it can draw. And when it draws, it just runs through that sequence very, 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 very quickly. With nothing in between. There's no measure, there's no layout, it's just the draw. And you'll see how much performance increase that causes soon. So here we go. The Honeycomb settings screen. You touch an item on it. Okay. Previously, this entire view group would have to be remeasured, re-laid out, redrawn. Just as you touched it, it created that alpha on the top. And it would do this. That was the old model. It drew the background, draw the panel, draw the selector, draw the Wi-Fi, draw the text box. In the new model, it can draw the selector, and then just draw the display list for everything else. Saves all the mucking about. But it does cause one problem, and this is the problem that you're going to find in your applications if you turn hardware acceleration on. Intersected dirty views are no longer invalidated for you. And by that, as you can see from that example before, we're just redrawing the display list for everything. We're not recalculating, we're not redoing anything else. So before, you invalidated a certain part of the screen, and because of that, you assume the entire view group would get invalidated and redrawn, which it would. Now it's not going to happen. So potentially you could be scrolling something on the right-hand side of the screen, could invalidate and expect the whole group to invalidate, but actually when you turn hardware acceleration on, the rest of that screen is not going to be redrawing. It's just going to be rewriting out the cached display lists. And if you want it all to redraw, you're going to have to invalidate all the view groups. And that's going to be the most common thing, or the most common cause for issues when you turn hardware acceleration on. Just make sure you're not just make sure you invalidate everything that you want to get redrawn, and you don't invalidate something that doesn't need redrawing. And then you can keep the highest performance and have hardware acceleration turned on. So it works with view groups as well. You can invalidate the view group, and it works up. Previously it would redraw the view group and redraw both the children again. Now if you invalidate a view group, first of all on the first draw we cache the display list. Now when you invalidate it, it just marks the display list part 30, the view group, and it redraws the top one. And this is that example we just saw with putting a highlight on top of that settings item. Everything inside it just gets drawn again. Okay, that was display lists. The second one of those hardware acceleration features is layers. The layers are super cool and easy to access. So here we go. We now have display list optimization already. We assume you know about display lists now, so that's fantastic. Well done. So now we have a button, and the button we've cached, it's been drawn once, we've cached the display list for that button, and whenever we want to draw it, we draw that display list to the screen. Fair enough. Now we add layers as well. And one more further optimization. And you're going to see the performance gain, just like you see the performance gain from display list, you'll see the performance gain from layers as well. So now we draw that display list to a layer and a layer to the screen. And there's three types of layers. No layer is what you're using at the moment. Software layer is going to render your view group, whatever you set your view, to render to an off-screen bitmap. And it will keep that, and then render that onto the screen. So every time you need to do the redraw, if you've got a software layer, it would have rendered it off-screen to a bitmap, whatever your view is, and then just be throwing that back onto the screen each time. And you can imagine that's much faster than even just redrawing the display list, but takes a load of Dalvik or heap memory. So you have to be careful with it. And the third one's the hardware layer. Just by setting view equals layer type hardware, you render directly onto the frame buffer, the GPU. And you use graphics memory. But it's super, super, super fast. So you get your performance on your hardware layers, and here's those timings I was talking about. So, software layer would take 10 milliseconds to render a list view. We now improve that for you by using display lists. So by adding a display list in front of your list view, we knock it down, 5-fold increase to 2 milliseconds. If you turn hardware layers on, your list view then goes down to 0.009 of a millisecond or 0.01. That's super fast. This isn't a fraction of a second, it's a fraction of a millisecond. Basically, the time it takes to get from the frame buffer onto the screen when you're on the GPU is no time at all. And you can use this to your advantage for a couple of different things, because once you've rendered to a layer, you can do effects on that layer. Say you want to rotate your entire view or change the alpha of the entire view. If it's on a layer, you can do that with the GPU directly in absolutely no time at all. Imagine if you hadn't got it on a layer, you'd have to do it for every single one of those views. So to re-render the Honeycomb menu screen in black and white. Previously, you'd have to redraw the whole thing, changing the alpha values and backing everything out. Excuse me. Now, you can apply a paint to a layer. So you draw the whole thing to a layer, and you just set the saturation of that layer to be 0. It does it for you, and it does it in no time at all. It does it in a tiny, tiny fraction of a second, because you've set the layer type to hardware. And then software layers. Better, more compatible, take the memory, and you can do animations with hardware and software layers. So these properties are layer friendly. Excuse me. I couldn't turn the mic on. And what layer friendly means is once you've rendered to a layer, you can then apply any of these things to it, and they're going to happen on the hardware almost instantly. You can rotate, pivot, scale. So, layers work with display lists. We'll find out. Layers work with display lists because they understand each other. So you have your button, and you decide you want to rotate it 45 degrees. Previously, that would be a whole load of work of remeasuring, laying out, everything. Now we mark dirty, and what do you think happens? We have the display list, the layer knows about display list, and you want to rotate the item, we just add a rotate into the display list, and we don't have to do anything else. Again, super fast. Happens really nicely. Display list and layers understand each other. If you want to do the animation, you set the layer type to hardware, you do the rotation, 180 degrees. And then that rotation is happening on the GPU. That rotation is happening in a fraction of a second. It's going to be super fast. But as I said, it's taking GPU memory up. So once it's finished, put a little listener on. As soon as it's finished, you know the animation is finished, you turn the layer type back again, you save all the GPU memory, and you get back into your normal running of your application. It's a really neat little trick. You can do it if the hardware is available, it puts it all straight down with the GPU, uses that acceleration. You haven't used the NDK, you haven't used Renderscript, you've just set one line of code, you've used layers. That's it. If you're not using hardware layers, be careful to set alpha. It requires everything to be drawn twice. Reuse your rendering objects. Don't modify their maths and data parts. The setup thing is quite interesting. If you try and build up a screen of items that are all at 50% capacity, I've seen it happen, and you put an item on that's 50% capacity, then another one on top, and another one here, and another one here, you're going to be able to see through all of those items to each other, but the effect that you really want, like you see on the home screen of Honeycomb, of either of these two, is you want all the items to be built, and then the whole thing to have 50% opacity. So we render it first once with a bitmap, and then we change the opacity to 50%. Sorry about the coughing, I don't know what's going on, it must be the air conditioning or something, but that is high performance graphics on Android. I think I'm just in time. So thank you very much, and if anyone's got any questions, please take the microphones.